So started the recording. Maybe we'll wait for a minute and then start. So before we begin with today's class, anybody has any questions from the previous class? So we had a break and yeah, so happy new year to everyone. If you have any questions, you can ask them by unmuting yourself or write them in chat. If not, I'll request you to keep the video and audio muted. Okay, so we'll begin. If you have any questions, you can put them in chat and I'll come back to them. And in the previous class we covered uh, some material. So these are the references. We discussed about them. We discussed about important information regarding this class, the class timing. So although I've booked the 3 days, we might not always have classes on all the 3 days. So I'll post a message like let you know before the class if you're rescheduling. Yeah, so the last class we covered the review of transmission line theory and the telegrapher's equations. So we usually have revision of the previous class, but since this was very basic and I had asked you to go through the textbook, so if you have any questions, you can come back to them, but we won't look at them now. So these whatever we discussed, some of it will be very useful in the next few classes while we write the codes. So today we'll begin with the introduction to computational electromagnetics and the finite difference time domain method. And so today again we won't be covering any codes, but the this introduction will be very helpful for you to uh, know how the computational electromagnetics is being used. We'll discuss some history on how the methods were developed and the advantages of method of moments and finite element method and the FDTD method, and what are some other methods which exist. So we'll cover that. And we'll begin with the introduction to finite difference time domain method, which we'll discuss the backward, and central difference scheme, some important terminologies, and then we'll begin with the codes in the next class. So this class is important for you to understand, you get to get into the mood of starting with the CEM. So before we begin, this quote I took it from the David B. Davidson book, where Professor Monk said, "Computations, no one believes them except the person who made them, and measurements, everyone believes them except the person who made them." So this is quite true. So I Nobody believes whatever you have simulated except you. And whenever if you do some measurements, you'll start doubting stuff. But since they have been measured, so everybody accepts those results. So with that, we start with today's class. So these are the popular Maxwell's equations, which we are all familiar with, and these Maxwell's equations are completed by the constitutive equations, where E and H are the electric and magnetic field, B and D are the flux, and rho is the charge density, mu and epsilon are the permittivity and permeability of the media. So this is what we are all familiar with. And the actual solutions of these equations will become complex for realistic problems, and we usually tend towards approximate results. And computational electromagnetics is what we tend to while when we try to make these approximate solutions. And CEM is a multidisciplinary field. So the core disciplines involved in this are electromagnetic theory, which we all, I believe, have the background, and numerical methods, which uh, so there's a question from Tej.
PPTs are
Yes, Tej,
visible. Slides are not visible, sir.
slides are not visible. Can anybody else
Mm,
confirm that?
No,
Yeah,
Anand,
it's
it's visible.
visible.
The slides are visible.
visible.
They are visible.
Okay.
I have to check my network.
Okay, yeah. Maybe you can try to
Yeah,
leave the meeting and join again.
yeah. Thank you.
Okay. Okay, thanks everyone. So, okay, so I hope it's visible to everybody else, and if not, maybe you can try leaving and then joining it. That usually solves the problem. So, we all have, I believe, the background of electromagnetic theory, and if not, I'll request you to definitely go through EM textbooks, watch a few lectures, and then come back to this course. Numerical methods is something which we'll cover in this particular course, only the related parts. So we won't go into the deep mathematics. So whatever solutions that we get, we'll assume that they are true, and we trust the mathematicians who did them. Um, the CEM is useful for geometric modeling and visualization. So these CEM methods were originally borrowed from the mechanical engineers, where they used to simulate stuff, and then we borrowed from them, and then we borrowed stuff from computer science engineers, use their algorithms to solve our problems. So we are borrowing stuff from other engineers to solve our problems. We went through this slide in the previous class, where we looked at the applications for computational electromagnetics. So yeah, so we frequently use them in developing and designing antennas, study of biological effects of the electromagnetic waves, medical diagnosis, design of MMIC, microwave devices, radars and imaging communication. So these are the popular examples of the areas where CM is used. Now, full wave CM technique. So in the previous class, somebody had a question of what is the full wave, what is quasi-static and quasi-static, and what is static. So we'll answer them now. So full wave techniques are where the Maxwell's equations are used in their like full-fledged ways. So we have electromagnetic waves traveling in space or through different media, interacting with different structures. Static and quasi-static. So static is when we only have the electric fields or the magnetic fields, and there is no wave propagation. Therefore, so we either have a steady state charges, and due to them we will have electric fields, or we'll have currents. So and we will have their associated magnetic fields. So these are the states where they qualify to be static cases. And in those cases, these terms, maybe I'll use a pen. So these terms become zero. And quasi-static is when these steady state charges are slowly moving, or the currents are slowly changing. And in those cases, these terms won't exactly be zero, but they'll be tending to zero. So we'll make approximations, and based on that, we'll solve the problem. So those cases qualify as quasi-static. So FDTD method can be used to solve all these cases. You can solve static cases, you can solve quasi-static cases, you can solve full wave cases. Now there are other methods such as asymptotic techniques, where we basically rely on the we use fundamental approximations on the Maxwell's equations. So I'm not an expert on these methods, but these examples are physical optics, geometrical optics, and uniform theory of diffraction. So these methods essentially are more based on ray theory. So if you can know, so for example, if you have a structure and if you use ray theory instead of the wave theory, so they are kind of the asymptotic methods. So I'm just bringing you this that there are other methods as well apart from FDTD, but we won't be covering them. And this is a field of its own study. So this you'll if you want to know more, you'll have to like I believe you have to go through text a lot of text for this. So if you're interested, maybe find a course, go through them. But yeah, so there are other methods as well. For example, the asymptotic techniques. And now the full wave techniques. So full wave techniques are potentially very accurate. The FDTD method, the method of movements, finite element method, and FDTD method. So all these methods are the full wave methods, and central to all these methods is the idea of discretizing some unknown electromagnetic property, which is typically the surface current for method of movements and the electric field for FEM and FDTD. So what we're trying to say is, for example, if you have an object which you are trying to simulate using either of these methods. So if you're using method of moments, then you will discretize the surface using triangular or tetrahedral meshes. And on these, on each of these element, you'll try to evaluate your uh, surface current. Yeah. You'll try to I'm trying to write current over here. So yeah, you'll try to evaluate surface current. And if you're using finite element method, so again, finite element method discretizes the whole space and we will have tetrahedral discretization. And over there, you'll discretize electric field. You'll try to evaluate that. Similarly, if it is FDTD, we will be using cuboidal meshes or square meshes if it is in 2D. And over there, we'll try to find out the electric field. We also can do it in terms of magnetic field or to use both. So this is what we're trying to say. We'll discretize the space and find out, try to evaluate an unknown electromagnetic property. It could be surface current or the electric field. Now, this process of discretizing is called meshing. So this term will appear quite frequently. This is both the discretizing term and the meshing term. So in FDTD, as I said, we use square meshes. So if there is an object like this, and if you take a cross section, so you will find there are these square meshes across it. And if it is FEM or FDTD, they will be either triangular meshes. Solvers also use hexagon or other shapes. And if you are discretizing the whole volume, then you will have tetrahedral meshes. So we'll look at the how the discretization look in the coming slides. And it entails subdividing the geometry into a large number of small elements. So each of these will be referred to as an element. So these may be one-dimensional segments, two-dimensional surface patches, often triangles, three-dimensional tetrahedral elements, as I said, and three-dimensional staggered grids, which is in case of the FDTD. So FDTD is we are saying that we are meshing in square or a cuboidal shape. FDTD is actually a meshless method because you typically you don't discretize the entire don't discretize the object. You basically divide the whole region into small spaces. So it is kind of meshless, but if you have to say it is being meshed, then we say that we are using square or cubes, not cuboids. And for one-dimensional segments, for example, in method of movements, if you're simulating a dipole antenna or a wire, then it's just small segments. It is a 2D plate, and if you are using method of moments, we will have triangles over them. So this is somewhat it will look like. If you have used HFSS, then when once you have designed your structure, you will be able to see either square or hexagonal meshes. So maybe you can open one of the solvers, HFSS, or so you will be able to see something like this. Or if you use CSP, by default, if you have kept your grids on, it will show you that this space is being meshed in cuboidal fashion, something like this. Generally, the accuracy of these methods is related to the discretization, that is the mesh size. So your results will become more accurate if you tend to discretize it smaller. So if you have smaller grids, you will be able to better approximate the geometry, find out fields in closed places, and then hence get better results. The finer mesh is the better accuracy of these methods, and the largest mesh uh, is limited by the computational. So yes, so if you are just so the question arises, if we use finer meshes, then we get more accurate results. Then why don't we uh, make the mesh or the discretization smaller? But if you discretize it very small, each of these element will take up some space in your uh, machine which is solving this problem. And if you have more elements, you'll need more space. So if and this particular space will be then limited by the RAM of your system, or even if you it might also be limited by uh, the storage space that you have, because these results will result into large volumes of data, and you must have enough memory to simulate them and enough memory to store them. Yes, yeah. So as I said, we have borrowed these techniques from the mechanical engineers in other fields such as structural mechanics. The mesh fineness is usually determined the requirement to resolve the structural geometry. So as I said, the mechanical engineers make, for example, different structures. For example, if they are trying to model this pipe, uh, they will decide how much is the resolution based on how accurately they model this particular object. But in RF, it is usually dependent upon the phase. If you're sampling the phase accurately. So as in the previous class, we discussed that if we are having a transmission line, and then we are taking a small element of the transmission line, and then we ended up with the approximate model of the transmission line. And this particular, we said that this particular discretization, if it is of delta z length, we say that this delta z tends towards 0. But but we don't have infinite memory for this particular length. So will have to take some finite value of this delta z, and we will resolve this delta z by keeping in mind that we have an we do not have we are approximating such that this the phase through this element does not change too much that affects our results. So we'll try to keep the phase accurate in this particular space. We usually tend to keep it below lambda by 10, this particular length, so that if you take this particular, for example, if this is your wave, and we are taking points on the wave, so we keep this so that we are taking at least 10 points on this wave, so that we are able to accurately model this wave, and there is not and there is we do not have too large of a phase change between these 2 points. And the smaller wave this delta z is, the more accurate will be the modeling of the phase. So I think I have said too much. If you I'll pause here and take questions that you might have.
Hello.
Yes, Anil.
Yeah, actually, thank you for follow up that what is full wave technique means. My question is that whenever we try to model a mm, particular conducting material and try to solve using a FDTD method,
Okay.
generally in HFS is something like that. We have some exciter which will try to excite the
Yes.
conducting material. So in similar
Yes.
way, in this computational electromagnetics, I mean, what will be the triggering point? How it will take excitation and how it compute?
Okay. So the question is how do we provide excitation in
Yes, yes.
FDTD?
Yes, yes, exactly.
So we'll answer this properly in the next class when we start writing the codes. So there in FDTD, for example, if you are taking trying we are, in this course, we'll try to simulate everything on transmission lines and everything. So we bring in a fictitious source. For example, if this is something what you're trying to simulate, this is your transmission line and you have a source over here. This is your source, and then it is terminated by some load. So this will be the first code that will write. And so you're asking how will we model this particular source? So
Yes.
what we do is
Usually we just try to
yes,
define it as a sinusoidal signal.
yeah.
Just
So in
sinusoidal signal.
FDTD, yeah,
Uh,
sorry. Okay, please continue.
Sinusoidal signal with some amplitude and phase.
Yes.
Is this the way that we try to define as a signal?
Yes, we do it as a signal. Yes, so it could be anything. So we'll start with the sinusoid, but since we are doing everything in time domain, I'll write it over here. We are doing everything in time domain. It could be any signal. You could do an arbitrary signal. You could do a sinusoidal signal. Anything that you can write in terms of magnitude and time. So we don't uh, bother about phase in time domain. It is basically amplitude and time. And you can write any signal. You can write your signal and store them as an array, and then you can feed it with time. And what this particular point, so we decide that we have a source and it is at a particular point, and over that at that point we just add the excitation. So this will become more clear when you write the code. So basically the methodology is you first define your space. You in your space you define which area has what media, and then you define choose a point where you want to include the source, and at that source you just feed the values. It is as simple as that.
Okay, thank you. Uh, okay, yeah, actually, okay, it will be prolonged discussion throughout the course. We can discuss. Okay,
Yeah, I
okay,
think
continue.
your
Thank
question will be more like better answered when in the next class when we start writing the code, and then if we can discuss more on this how we are like, doing the excitation.
Yeah, okay, thank you.
Okay. And any more questions? And anyone else having similar questions or any follow-up questions on this? Okay. So we'll proceed then. So this is a table comparing the three popular methods. So we'll go over each method in quickly and discuss about advantages and disadvantages of each method. So it is summarized in these two tables. We are doing FDTD in this particular course, which uses differential equations, and it is a time domain method. And FDTD does not require a radiation condition, but we will need absorbing boundary conditions or termination of other sorts. method of move. So sorry. So it's a so we the method does not have an radiation condition. So we use absorbing boundary conditions, the other kind of termination. If you are doing it in 2D, 3D, you use a perfectly matched layer PML. This is discussed in one of my previous courses. In this particular course, we will terminate with the source sources for and with source impedance and load impedance. Similarly, finite element method also does not have a radiation condition, and hence you have to terminate your space using some conditions, which if you want to read more on FEM, you'll probably have to borrow textbook from library, or if you have one, go through it. Method of movements, it already has a radiation condition included in the formulation. So, for example, if you're simulating something in method of movements, for example, this is your uh, some helical antenna. If you're doing, you don't have to terminate the space. So whatever the space you're simulating, you just discretize this helical antenna and solve it using your matrices, and then you get the results. You don't have to bother about the space around it. But if it is finite element method or FDTD, uh, you mesh the entire volume where apart from this helical antenna, you have to mesh the nearby region as well, and then you have to terminate the region as well. So if you have used HFSS, you must you will remember that when you design an antenna and then you include a radiation box, something like this across around the structure which you're simulating. Well, if you have an object here and you give some gap between the area so that you get your correct results. Similarly, in FDTD as well, if we are simulating a particular region, we have to make sure if, for example, if this is 1D, then we have to make sure we terminate the boundaries correctly. Otherwise, when the wave reaches here, it will reflect back into the space. And the method of moments is if you're simulating perfect electric conductors, it is very good. Um,
Uh,
if you're
Anand,
Yes,
could you
Ankit.
hear me? Anand, which type of boundary condition mainly we used for this transmission line? Is it Moore or something else?
Um, So in this particular course, we won't be using Moore's or absorbing boundary conditions. We'll terminate them with load and source impedances. So uh, we'll
Okay.
solve voltage and currents at the end, and then modify the nodes at the last node such that it includes a resistor or inductor, so that we can terminate the circuit with, for example, a 50 ohm load or 100 ohm, so that we have that flexibility. If you use Moore, it will just so for the class Moore sub you can study on Moore's absorbing boundary condition, which is very popular for 1D implementation. So in what Moore's 1D implementation does is it takes the last two nodes and solves like evaluate the field such a way that whatever field travels in this direction does not come back. So this avoids reflections, but we won't be looking at Moores in this class. If you want to you see Moores, you can refer to the other my other course. In this particular course, what we'll do is we will have a circuit which will always be terminated by a load impedance. And this load impedance will be included in the formulation of the voltage and current, which we'll be using for the update equations.
Okay, thank you.
Yes. Okay. So we'll continue. Method of movements is very good for solving perfect electric conductors and homogeneous penetrable media. But for inhomogeneous penetrable media, for example, if you have a structure which has varying dielectric permittivity as different places, method of movements is not the best. We'll see in coming slide that method of movements meshes only the surface. For example, if you're trying to solve this particular region, it will only mesh the surface, And since it is only meshing the surface, it becomes hard for the solver to know how the fields are varying inside. So for that case, you can use method of moments to solve these problems as well. But in that case, you will again be meshing the entire volume. So method of moments has the benefit that even for 3D structures, you use 2D meshing. But if you end up meshing the entire volume, it's better to use FEM or FDTD because they already do it and are a faster method. So method of moments is not preferred for inhomogeneous media. For homogeneous penetrable, it's all right. For finite element method, it's differential based on differential equations. It is frequency domain method. We saw that it does not implicitly include radiation conditions, so we have to make sure we terminate the solution space. It's not very good with perfect electric conductors, but you can solve it anyways. It's very good with homogeneous or inhomogeneous penetrable media because you are meshing the entire space, and then for each tetrahedral mesh, you can assign some permittivity and permeability values, and so you can solve them quite easily. Similarly, for FDTD, it's a differential and it is time domain. We use absorbing boundary conditions, perfectly matched layers, or some other sort of termination that we'll see in this course. It's not very good with PECs, but you can use you can high sigma values to solve them. It is very good with homogeneous and inhomogeneous penetrable media because you're discretizing the entire space. So this was the just the first table. We'll discuss in more detail in the coming slides. Um, so these are for the open region problems. For guided wave problems, where you have we have a source again. The method of moments and finite element method, they are satisfactory for wideband solutions because they solve at individual frequencies. They are frequency domain methods. They will solve at each frequency, and since most of the devices, for example, if we design an antenna or a filter, uh, they are usually narrowband devices. So it's all right if we solve for example 101 frequency points or even in 500 frequency points. It's all right for our computers. So it's all right. Even if it is wideband device, we can go up to 1,000 points and no problem, and it will be solved in seconds. But if your device is a very wideband device and you have to solve, for example, 1 gigahertz to 100 gigahertz, then you'll and with sufficient resolution, then you might end up solving a lot more frequency points, and these two methods might not be very efficient. In those cases, FDTD is very efficient because since it solves in time domain, you can just send an impulse function, which qualifies as like a flat response in frequency domain, and then you can easily obtain your S parameters or wideband characteristics. So FDTD is very good for wideband simulations. For guided wave, if you're just solving PCs, it's all right because um, your term boundary conditions will then become PC, and in those cases you can easily terminate your boundary. And or again, so we have already discussed this thing. Okay, so we'll go through detail in those points for each method. Before that, we let's look at how we are discretizing in each case. So for method of movement codes, they use triangular meshes. So you can see on this, if you're discretizing this sphere, we're using triangular meshes, and triangles actually give us very good approximation of all kinds of surface. For example, if it is a cuboid, even in that case, you can use triangles and get good approximation. If it is, for example, an irregular uh, structure, even then triangles can be used. The triangles need not be equilateral or of the same dimension. It could be of any shape. Best are the scalene ones. So and method of moments tends to discretize only the surface. If you're using FDTD, we use regular brick or cuboidal mesh. So if it is a 1D case, and in both the cases, method of moments, all of them will use segments. FDTD will also use segments, but if it is a 2D case, it will become squares. And in method of moments, this will be triangles. And for volumes, MOM does not discretize volume, and if it has to, it will look something like this, which is same as FEM. FDTD uses bricks, so you can see that you will need much more elements to accurately model this particular sphere. So a number of elements increases in FDTD. And FEM uses tetrahedral shapes, so you can see on the surface it looks like triangles, but inside it is these tetrahedral shapes. So these look somewhat like this, and I don't know if I'm able to draw them correctly. So this looks like this pyramid shape. It will have 4 points. This is how we discretize FEM codes in FEM. And again, so these can model the irregular shapes or curves more accurately. So FDTD has a disadvantage, but we have found out different ways how to tackle this. Um, but since we won't be dealing with 3D structures in this course, we won't be bothering with them. Okay, before we begin with method of movements, if anybody has any questions on this.
Hello.
Yes, Sudeep.
Actually, I have seen that in HFSS or some other software, there are some techniques called hybrid techniques, which uses combination of FEM and MOM or something like that. So actually, how does that work?
Okay, so your question is a little advanced for this course. So how do they work? I think for a better answer, I'll have to look it up, but they tend to, for example, when these solvers use templates, and when you describe which outputs you want, they will choose either of these methods or use a combination in which for some, for example, if you're trying to solve for charge density or current, they will use the method of movements, for example, and if you are trying to solve for fields, they will use FEM, and maybe use to get them together. So I'm not very sure how exactly they combine these methods because I've never worked with them. Maybe I can study it for you and give a better answer in the next class. I'll also recommend, since you had this question, maybe you can also look up how they work together and share what you read with the class as well. So
Okay,
maybe follow up with me in the next class. I'll look it
yes,
up.
yes, yes. Okay.
This reminds me, in the previous class somebody asked if we have the transmission line and we are discretizing them and we are using RLGC values, and so we'll have another cell next to it, and these two might be coupled, and we might have more complicated, uh, maybe a unit cell than this simple one. So I asked around, and the best answer I could get was, since this unit cell is very small, as this delta 10, the delta z tends to 0, uh, we won't be seeing the effects of this coupling will be negligible. Um, I so we need some finite length for the coupling to happen, and since these are this length is very small, we won't be seeing any effects of them, and hence we are good to go with this particular unit cell design. So I hope I have answered your question. If you have any follow-up questions, you can ask them or get back to me via email as well. We can discuss this. Okay, so we'll proceed with method of movements, some discussion on it. And since we have a lot of slides to cover, we'll move a little quickly. So in the method of movements, the radiating scattering structure is replaced by the equivalent currents, and these are normally surface currents. So we have been discussing that when we are trying to solve a problem with method of movements, we discretize only the surface and not the volume. And once we have discretized the surface, what we do is we solve for surface currents using the method of movements on each of these elements. And once we have the surface currents on each of these elements, most parameters can be derived from these values. And if we have inhomogeneous electric bodies and we are still going with method of moments, we discretize the entire volume by using the tetrahedral mesh, and then we again solve for the currents on uh, these meshes, and then we try to solve. And this will be computationally very expensive. The surface current is discretized into wire segments or surface patches. So if it is a 1D structure, we just discretize them like this, and then we solve for currents on these. So this is what in 1D, and 2D and 3D, we use these triangles on the surfaces. So when we have discretized them, a matrix equation is then derived representing the effect of every patch on every segment. And this interaction is computed using green function. So let's just ignore this because we'll have to get into a lot of details if we are going into this. So what is been trying to say is, once we have discretized the entire the volume with this, for each element we will have this surface current value and other variables, and each of these variables will be then filled into a matrix. And this matrix comprises of interaction of each of this triangle with the other triangle. So if you have a very large structure and you're trying to discretize, so there could be a triangle, there could be triangles over here, there could be triangles over here. So each of these triangle will interact with this triangle, and so the interaction of each triangle with the other triangle will be noted down in this matrix, and then you will have your unknowns, which will be equated to some boundary conditions, and you solve these interactions will be filled over here. Your unknowns will be here, and you have your boundary conditions, and then you do the inversion and stuff and get the values for your unknowns, which are over here. So this is how we go about in the method of movements. Uh, the relevant boundary condition is then applied to the interactions using a set of linear equations, which linear equations you can write them in matrices. Yeah, and so the resulting matrix, which must be factored, is fully populated with complex values entries. So these entries could be complex values as well. And the typical matrix dimension ranges from some hundreds for small antenna problems to several thousand. And the upper limit is imposed by computation limitations. So if you have less memory, then we use larger meshes and hence less number of these triangles, and then try to make a matrix which our PC can solve. If you have more memory, then you can use finer meshes and then see the effects of how finer mesh do you have to do to get your converging values. Additionally, method of moments has been applied in frequency domain. Yeah, there are some time domain implementations, not very popular. We won't be going through them. And these this what we are trying to solve will include this term like this, e power j omega t, and so it will be solving for each omega. So we solve for each frequency, and then we can change the frequency values and get results. For example, if you're trying to solve for S parameters, then you can solve for one frequency, then for the next frequency, then for the next frequency and next frequency. And then this is how you might uh, get your plot and see where your resonance is. Okay, so any questions on this? We'll discuss the strong and weak points in the next slide. Okay, so we'll proceed then. Let's look at the strong points of method of moments. The method in method of moments, there is efficient treatment of highly conducting surfaces. So it's very good for PCs because we're solving for charge, which we're solving for currents and charge density, which is and since we are meshing only the surface, and if it is PC, it is solved in the best way. Only surface is meshed, no air region around has to be meshed. So we don't have to care about the boundary termination. Um, and if you're solving for wire antennas, the treatment is more efficient since it is a 1D problem and you don't have to even worry about meshing. You just take your wire antenna, it could be of any shape, just discretize them in length and then solve for the effect of each length on the next value. The method of moments automatically incorporates the radiation condition that we have already discussed, and we don't have to bother about meshing the outside region of the whatever structure that we're simulating, and the far field condition is automatically included in the method of moments formulation. So to give you a gist, for example, if we are solving for the effect of the radiation from this particular device under test, the equations that will solve will use the effects of 1 by r and 1 by r square. And those values will be included in the formulation. So the far field condition and everything is sorted in this particular method. The working variable is current density, which is a very important parameter, antenna design parameter, because impedance, gain, radiation pattern, etc., are all can be found out once you have calculated the current density. And in most cases, you will have very straightforward numerical integration. We have come very far in these mathematics, so you just can use any of the methods that are available. One point, like I think they're called quadrature integration or something, trapezoidal integration. I'm forgetting their proper names, but these are the methods which are available, which you can use for your numerical integration. Uh, there is something called Sommerfield potential, which can be used for efficient formulations, which for stratified layer media. So and this is for the inhomogeneous technique. If we are doing solving inhomogeneous problems, uh, there are some formulations called Sommerfield. I'm not very familiar with this method, but it allows you to solve layered media in method of moments. So if you are doing if you have to use method of moments, you probably need to study the Sommerfield's equation, and the Green's functions as well. So this is something we did not discuss. So the US had developed some solver based on method of movements for their defense applications, and later they made it public domain. And once this when this particular solver became public domain, so this was called NEC2. And once this hit the public domain, there was a lot of research, and many solvers were built on this. So this is one of the reasons of the popularity of this method of moments. Now let's look at the weak points of method of moments. Uh, the method of moments does not handle electromagnetic permeable materials as well as differential equation formulation. So if, this is especially true if it is inhomogeneous. We have already discussed how this method becomes terrible if you are trying to solve a region which has different electric properties inside, because we are just meshing the surface. And if you mesh only the surface, you consider that the entire region is of one particular material. But if it is graded, or if its permittivity changes across the region, you will have to mesh the entire volume. And we saw that each element interacts with the next all the other elements. In that case, the matrix will become very large, and this will become too much for a simple processor to handle. While to compare with where a finite element method, where also you mesh the entire volume. In that case, the dependence is only between the neighboring cells, and hence the matrix is very small and sparse. But in case of method of moments, each element interacts with all the other elements, and hence the matrix is very large. So this particular method does not handle inhomogeneous media. A method of moments also does not scale gracefully with frequency. So the scaling is of the order KD and power 6. So for smaller frequencies, it's all right. But if you are using larger frequencies, the computation will become more complex. It will take longer. So, uh, for example, if you double the frequency, since the order is of 6, 2 power 6 will give you 64. So your runtime will become 64 times long. So, for example, if you're solving a problem in 1 second for one particular frequency, this will become 1 minute. For if you double the frequency, and it will become an hour or so, something for if you make it. If you double that as well. And so this is not very good if you're trying to solve for higher frequencies. And there are some method of moments formulations based on magnetic field integral equations, which require surfaces to be closed, which is impractical. So a lot of problems, for example, if you want to simulate a parabolic dish, you can do that in using method of moments. But if you're using magnetic field integral equation based technique, which is again based method of moments, this won't be possible because your surface is not closed. Okay, so these were the strong and weak points of method of movements. Any questions on these? Okay, so we'll proceed with the finite element method. Okay, so before that, the FDTD method. So like finite element method, the FDTD method is based on partial differential equations and does not need green function, which is something you have to do if you are using integral equation based stuff. So you don't have to do a lot of mathematics. So this green function stuff is a lot of maths, and you skip that if you're using FEM or FDTD. But unlike FEM, FDTD method does not use something which is called variational functionals or weighted residuals. So these are the two methods in which the FEM uses. So FEM, what it does is if you're trying to solve some unknowns, you write your unknowns in terms of some function, and your function will be some polynomial of some orders, and then you solve this, you find the maxima or minima of this polynomial, which gives you a solution to this function, and which is then used to again get back the values of the unknown. So this is how you go about using variational methods or weighted residuals. Also in the weighted residuals, you will have a polynomial with coefficients, and then these coefficients will have some weights, and then using those you get the value of the unknown. So this is how you go about in the FEM, and in FDTD you don't have to write any more functions. It directly approximates the differential operators of the Maxwell-Curls equation. So very briefly, what FDTD does is you have a simulation space, you discretize it. We'll see about why we are discretizing like this. And then we try to solve electric field over here, electric field over here, electric field over here. Use the values of electric field to find out magnetic field over here, magnetic field over here. And similarly, use and magnetic field over here, magnetic field over here. And then use the values of these two magnetic field to find electric field values over here, these two to find electric field value over here, electric field value over here. And then when you have these, then you can find out the magnetic field value over here. So everything happens very locally. You don't have to solve any integral or any big problem. You just add and subtract these values, and that's all about the FDTD method. So it's very simple. Hence it is very popular among students. The electric field and magnetic field values are computed on a regular grid. So this is something what the grid looks like with marching on in time discretization. So we'll have to, okay, let's first read this. With field components being offset by S by 2, where S is the discretization space, delta S is the discretization space, and relative to each other, and electric fields are evaluated delta this t by 2 apart in time, where S and T are spatial and temporal discretization. So I'll probably need more space than this. Maybe do I get rid of the markings? Okay. Let's start fresh. Okay, so so in FDTD, the grid, so this is your simulation space, and then we start discretizing. It says the field components are offset by S by 2. So let's say that this is a 1D problem and this is your space axis and this is your time axis. And it says that E and H field are offset by S by 2. So if we are calculating electric field over here, the magnetic field should be somewhere around here, and then which is S by 2 length. And then the next electric field will be over here. which will be again S by 2 from the magnetic field, which is over here. And similarly, we will have some magnetic field value over here and the electric field value over here. So where basically one S distance away from the electric field values and one S distance away from the magnetic field values. Now it says that the electric field and magnetic field values are T by 2 apart in time as well. So if you're moving with time, the electric field values and the magnetic field values, they are T by 2 distant apart. So this particular H value is not exactly over here. It is somewhere over here. So it is T by 2 away from the electric field as well and S by 2 away from the electric field as well. So it will be calculated over here. Similarly, this H value will be actually calculated over here in time. Similarly, H value over here. And hence the next electric field value will be calculated over here. Similarly, the next electric field value will be calculated over here at T distance apart from the previous E field. And again, the next H value will be calculated half away, T by 2, S by 2 away from the electric field and T by 2 away from the electric field. So the next H value will be somewhere over here. So this is how we will calculate the E and H values. And in this course, we will use voltage in place of electric field and current in place of magnetic field. So the grids will look same, but these variables will be replaced by these variables. So I'll pause over here and take questions because this is very crucial. We'll discuss this again when we discuss the E grid, which will come later toward the end of this class. But it's better to be sure that we are getting this.
Hello.
Yes. Yes, Urbi.
Yes, sir. I have doubt in this line. This permits a scheme which uses first order numerical differentiation to provide second order accuracy. What is the meaning of this?
Oh, so we have come not yet discussed that. Um,
Okay.
so we will discuss this particular towards the end of this class where we will study the forward difference, backward difference, and
Okay.
central difference scheme. So when we discuss all the three schemes, we will see that these two schemes,
Ah,
they have first order they have first order accuracy, and the central
oh.
difference scheme will have the second order accuracy. So
Okay.
we'll do the math in a later in the latest part of this class.
Got it, actually. Okay, thank you.
Okay. Okay. Any for more questions on this?
Hello.
Yes, Sudeep.
Yeah, Anand, I have just one doubt. This there are two divergence equation in FDTD in Maxwell equation as well, right? So in
Yes.
FDTD we do not generally discretize them, right?
No.
So what is the reason for that?
In the FDTD scheme, why do we not discretize?
Yes,
Is
only the curl equation we generally discuss, but we do not
yes.
we do not discuss about the divergence equation. So actually, this doubt I am having. So why don't we do that as well?
Okay. Um. So the scheme is built upon the discretizing the curl equations, and the divergence equations basically are included when you like try to include any excitation or source is is what I have felt. So I'm not very particular. like I'm not very sure with this answer, but we don't need to, and hence we don't do it. And they are included in the scheme implicitly somehow. I'll probably have to read on that as well, but we don't do it because we don't need to, is what
Okay.
I'll answer.
Okay. Okay. Thank you.
Okay, so I will ask again if we are sure that we understand this. We'll discuss this again, but this is very crucial. I guess this is all right with everyone. So the next point was that as Surbhi asked, this permits a scheme which uses first order numerical differentiation to provide the second order accuracy. We'll in coming slides we'll see that we can use the three different schemes, forward, backward, or central difference scheme, and we will be using the central difference scheme, which will be second order accurate. And why this will happen will become clear when we uh, uh, like expand the Taylor's expression for this scheme. And so this is another important line, that this FDTD is the only widely used computational method which operates in time. So the methods MOM and FEM, which are the popular methods, they are frequency domain, and FDTD is the only popular time domain method. The FDTD method is an explicit method, so which it will become more clear as we solve problems. So the explicit means that we don't there is uh, no matrix equation is set up. You can also do it implicitly. So there are methods to solve the FDTD method implicitly. We won't go over them. You can after the end of this course, you will be able to read these papers and understand them. But we will be using the explicit scheme where we don't have to set up any matrix equation. And as you have seen that once we have the space defined, we can just use the previous values. For example, if you're trying to find the latest electric field value, and this can be calculated using this is the latest value. This can be calculated using the previous electric field values and the previous magnetic field values. And we don't have to set up any matrix to calculate this. So hence, this is an explicit method. And this has a great advantage of keeping the operations very simple, essentially just a stencil involving differencing neighbors in space and time. So what we're trying to say is, in this particular space, for example, if you're trying to find out this particular node, and this can be calculated using this value, and this value, and using the three values, we can calculate this. And if you use this particular stencil, if you just move the stencil over here, for it's if you can just move this stencil over here, so we can calculate this value using this value, this particular value, and this particular value. So this is just the stencil. This is how we are updating. We'll use these three value and get this value. So this that's about it. So this keeps things very simple. Each value is updated in one iteration, and then we can move to the next iteration and get the values. Now, this the limitation of the FDTD. There is an upper limit on the time step, and it turns out to be rather less than the Nyquist sampling criteria, um, which one pays for the simplicity of this method. So since this method is very simple, it must have some disadvantage. And one is the upper limit on the time step. So uh, you can this particular time step, you cannot make it large, because if you make it too large, you will end up with a bad code which breaks up while simulating, and you have to keep this t sufficiently small so that things are updated. But if you keep this t, but since this value, if you limit on this value, and hence and you need to solve this particular simulation space, for example, 1 second, like your simulation time for which you want to simulate a structure is 1 second, but you cannot keep the your structure limits you to keeping this particular simulation time, the minimum this delta t to be 1 millisecond. Then you will have to solve for 1,000 steps. So which is a lot of steps. For example, is in particular case. And you cannot just arbitrarily increase this delta t value to keep this as 1 second so that you just do one iteration. So there's a limit on the time step, which leads you to deciding the number of iterations you have to do. So this time step limits you if this time step is very small, the number of iterations will be very high, and hence your code will take longer to run. We'll discuss in detail how this particular limitation is put by studying the Courant limit. For right now, you have to know that this particular limitation is defined by the Courant limit, which for 3D cases is limited to this value. And for 1D cases, t should be less than s by c, where c is the velocity of light. And s is the discretization in space, and t is the discretization in time. So the discretization in time should be smaller than the discretization in space divided by the velocity of light, or this could also be the velocity of the wave in that media. So this is the limit, and due to this limit, we have to run longer. So I'll pause over here and take questions on this. Yes, Benjamin.
Yes, thanks, Prof. Can you please just explain the difference between the one on the current limit of t less than s divided by the root 3c versus the t less than s divided by c? I just didn't get what's the difference of those two cases. Yeah.
Okay, yeah, I'll do that. So maybe okay. So we'll discuss this properly when we discuss the Courant limit. So I just said that for the Courant limit dictates what this limit will be on the time step, and for 3D cases, this is t less than s by root over 3c. For 2D cases, this is t less than s by root over 2c, and for 1D cases, this is t less than s by c. And this occurs because, just to give you an idea, for 3D, when we are trying to solve, it involves a cube, right? And so the length of this diagonal, if you want to calculate, so this if this is a cube, this is s, all the sides are s. This length of this diagonal will be root over 3s. So this 3 will yes. So this is somehow related to this. So this will probably become a homework, but how this 3, 2, and 1 comes in. But this is how it is related. So we're taking the length of this diagonal. Similarly, if this is a square and length of this s is the side, this becomes root 2s, and this root 2 is how affects the 2D case. And if it is just a line, this is s, and hence this is just s. So we have one over here. So this is how it corresponds to. Um, we'll see the derivation of this particular thing later in the class. So if we want to generalize this for an n-dimensional space, this will become T root over S by root over N C. I hope this was able to give you some idea of how this number is coming. Any follow-up questions? Okay, so I guess that is clear. If you have, so you don't have to worry about the Courant limit. We'll discuss this later as well. So I have said this for a lot of topic because we're just uh, looking at the summary of the three methods. We saw a method of moments. Now we're looking at the FDTD, and we'll look at the advantages and disadvantages of FDTD and then FEM as well. And then we'll start with FDTD. And when we start with FDTD, we will discuss all the important things that we need to know to write our codes. So the FDTD is has a lot of features and drawbacks as well. One of them being the cuboidal mesh for spherical or irregular shapes, which is not very good. The limitation on the time step is no, is a drawback, but the attractive features being the implementation is very simple. You use the simple stencil to calculate the values. So all methods have their own advantages and disadvantages. We looked at those for method moments in the previous slides. The another advantage being that DTD is capable of simulating wideband sources. So if you remember your Fourier and Laplace transforms, uh, the Fourier transform of an impulse function is somewhat like this. If you have a sinc function like this, its transform is a rectangular pulse like this. So if you give this particular excitation, so this is impractical. So the nearest one is this thing. So if you provide a Gaussian, a very short Gaussian pulse, it can also translate to a very wide band Gaussian pulse. So if you use these kind of excitation, you can easily get wideband results using FDTD in just one run. While in case of the frequency domain method, you will have to simulate for each particular frequency. So this is a great advantage for using this particular method. But this usually does not help a lot because majority RF devices operate over narrow frequency band. So we usually call different devices as this is an S band device, or this is an X band device, or this is a Ka band device. So usually devices work in a very narrow band, and there are not a lot of wideband devices. So this the no, it's not usually an advantage, but yeah, but if you are designing a wideband device, FDTD is the best method to simulate it. Um, and for example, if your device has a high Q device is, for example, if you're trying to if you have a resonator and it has a high Q, so this particular the resonance area, for example, at the particular frequency, it will be very sharp, and you will and for frequency domain methods, you just solve at this frequency and this frequency and this frequency, and you know that your resonance is at this frequency and this is your S parameter and stuff. But for FDTD, in that case, you will have to keep your delta t small enough so that you resolve the frequency so that this calculates your delta f very finely so that you can achieve this resonance. So if you don't have sufficient resolution, frequency resolution, you might even miss this resonance. So I'll give you an example. For example, if particular resonance and this particular and the frequency, this is F1, this is F2, and this is F3 over here at 3 points. In frequency domain, you can easily find out if you're since you're solving at this delta F, you solve at this particular frequency, you will get the correct value. But if your delta T was not sufficient enough to encapsulate this particular delta F gap over here, you might just miss this particular point at all, and you might not see any resonance, or you might see something like this, but because you missed this frequency point over here and this resolution was like this and you did not solve at this frequency. So this is an issue for high Q devices. You have to make sure that the frequency resolution is sufficient, and this is dependent upon the delta T that you take and the FFT that you do. Because your method is time domain, you will obtain voltage current values in time domain, and then from moving from time domain to frequency domain, you do an FFT or related techniques. Many systems exhibit dispersive properties as well, and which are mostly uh, real electric and magnetic materials. So dispersion is, I hope you guys remember that dispersion is the effect of like the material in which uh, delays affects the propagation of wave. So, for example, if you send a Gaussian pulse through a dispersive media, some of the frequencies will arrive faster and some of it will arrive later. And so this particular Gaussian pulse could be spread out like this. So this is something which happens due to dispersion. And if your media is dispersive for frequency domain solvers, this is included. So this particular thing is the amount of dispersion will is a function of frequency. So for each particular frequency, the wave velocity will be different. And this is very normal for solving in frequency domain solvers because the F1 will have different velocity and F2 will have different velocity due to dispersion. And since you are solving at individual frequencies, this velocity is all right. But if you are solving in a time domain solver, all the frequencies are sent together and this will have different velocities for each frequency. And this complicates stuff, and hence you will have this becomes a convolution problem because this particular effect is encapsulated by the permittivity, and since permittivity is multiplied to the electric field, and so this particular relationship. If the epsilon is different for different frequencies, this will and it is a multiplication. This will become a convolution in time domain. So we in this particular course we won't be seeing dispersive media, but at the end of this course you will be able to follow how to solve this particular question, so you don't have to worry about it. And if you want to study more on this, this particular textbook by DM Sullivan, it has example codes as well on solving how do we solve dispersive media. So you just have to do one particular convolution and then you get an expression which you multiply with the electric field, and then you calculate the displacement current and then update the electric field. So what I'm saying sounds very complicated, but it isn't. It's fairly simple, but it's not very straightforward as in case of the frequency domain solvers. Okay, so we have already we just discussed that in frequency domain, this is very simple, and in frequency and in time domain, we have to do a convolution. And many techniques have been proposed to implement this. Some of them, so the DM Sullivan textbook this uses Z transform, and there is a paper by Levin Savici which discusses Z transforms, auxiliary differential equations, if I remember correctly. And there's some method called PLRC, which is some, I don't remember the full form of this particular method. So in that, but this is an IEEE microwave magazine paper, which discusses these three different methods for handling such dispersive media, and also this paper particularly serves about negative permittivity and permeability. A very good paper. You can go through this as well after you have finished this course, because before that you might find it tough to read. So any questions on what we discussed now?
Hello.
Yes,
This
Sudev.
yeah, this relationship between quality factor and time step is not really clear. Can you just explain it again?
Yeah, sure. So if your device has a high quality factors, it resonance will be very sharp. Okay. Um, and this so you need sufficient frequency resolution to get that. So if, for example, if you have a device and it's and you're solving at, for example, in this much time frequency resolution, okay, and so what you get values are like this. So you might understand your device is not resonating, but probably the resonance was in between of these two methods. And since you're designing this particular device in frequency domains, a device like what you're trying to simulate, you probably did some mathematics and you know it should be around this particular frequency. So for frequency domain solvers, you can just solve at this frequency and the nearby frequencies and see the resonance. But for a time domain solver, you will be using excitation, like a wideband excitation, for example, an impulse function or a sinc function. And if this particular, if and your code will be dependent upon some delta t, uh, and this delta t will actually help you resolve the that particular frequency, which is delta f. So this particular delta f will be determined by the time step which you choose for your code simulation. And if you did not choose this delta t correctly, this delta f won't be sufficient enough to catch this particular resonance. So you might end up with just this particular S parameter instead of getting the dip at the right place. So what I was trying to say, you have to choose this delta t sufficient enough that you catch this particular resonance.
Okay, thank you.
Yeah, any more questions so that we can proceed? Okay, then we'll proceed. We've been discussing about the FDTD for uh, past 2, 3 slides. Let's discuss these strong points. So we'll just conclude what we saw right now. So exceptionally simple implementation for a full wave solver with least order, like, so you essentially we're trying to say that we have to do less work, and this is still a full wave solver, the FDTD method, which is compared to the method of moments or finite element method, which require much more mathematics as compared to the FDTD method, where you don't really do any real mathematics. You just do some different scheme and then calculate using this template. So this is all you do. And it still gives you good results. So and for FDTD, once you have written your code and you have a simulation space, you can simulate any structure or with multiple structure having inhomogeneous regions and everything, and you can still do it by yourself. But if you go towards these two methods, they will become more difficult because you will be involved in much more mathematics to solve complex problems, and doing all of them by yourself for each particular case is not like practical. But for FGTD is it's all right. You probably need to spend more time in while discretizing the space, and that's it. The loop which you will write will have two lines, and when they execute, they will still give you good enough results. Um, like FDTD method, with same as finite element method, they have very straightforward treatment of and homogeneities, because since you are discretizing the entire space, each particular inhomogeneity will be encapsulated in that particular element, and that particular element will get the epsilon and mu values, and you're good to go. Fairly accurate geometrical modeling ability, but not as good as FEM, since FEM uses tetrahedral shapes. You won't get as good approximation. We saw in this sphere example. The brick example for the FDTD was not as elegant looking as for the FEM or MOM. And since this method is the time domain one, wideband data are potentially available from one run. So in just one run, you can simulate from 1 GHz to 100 GHz in very small time with sufficient memory. But if you have to do it for the method of moments or FEM, you will, and with the same delta F resolution, it will take much longer. Scaling behavior is similar to other methods. It is f to the power 4, but if you account for dispersion, so we won't get into this. Just remember this term, like these orders. So this is a power 6. So it is similar to MOM or FEM, and the so this also scales very badly, but not as bad as MOM, because this is still a wideband method. So for wideband systems, this is very attractive, since the other methods have implied that they have f power n multiplicative term, not showing in the preceding sections. Yeah, so these two are more based on how you calculate the computational complexity, but for FDTD, since it's a wideband system and all the results you're getting in one run, it's all right. You don't have to run the particular code snippet for each frequency every time. Hence you don't have to bother about the time it takes. And if we are to if you go towards the 2D and 3D implementations, then uh, there is something called perfectly matched layer. So this was given by Beringer and then improved by like other scientists as well. So perfectly matched layer is something very popular in FDTD, and you will be using them to terminate your implementation space. For example, if it is 2D and you are simulating this particular region, you will have PML over here, here, and here, so that there are no reflections from these boundaries. And similarly for 3D, PML will be at each surface, so that there is no reflection from the boundaries. And before PML was introduced, FDTD was not very popular because it did not have a good terminating space. And so if you're solving a particular problem, you would use a very large boundary and stop your simulation before your wave reaches the boundaries. But after the PML was introduced, this particular problem has vanished, and yeah, this method is as good as any other. Now, for the drawbacks, we have inflexible meshing. That is, FDTD is kind of a meshless method because we have these cubes which you don't actually make it in on the surface. Your code solves it in such a way that these are cuboidal, and people have tried doing other kinds of geometries, but they have not been very successful with FDTD. And since because they are cuboidal or square, they do not accurately model the curved spaces or, for example, spheres. There are some uncertainties about precise position of boundaries. So we saw when we were making the E grid that we are solving H field over here and E field over here and then H field over here. So we find the H field over here and then E field over here. So there are some uncertainties because we are not solving the electric field and magnetic field at the same points. We're solving them at different points in space and time. So there is some uncertainty. If you are to give the value of electric field and magnetic field at the same point, you won't be able to do that in FDTD. Now, the dispersive materials require considerable effort to implement correctly, but this is possible. So, as we discussed, there is the method of Z transforms, auxiliary differential equations, or I think it's called ADI and not ADE. So you can look it up, and PLRC. So these there are three methods, and there could be.
Anand, it's ADE, it's not
It's
ADI.
ADE. Okay. Oh yeah.
Yeah.
Thanks, Ankit. Yeah, I got confused. So there are three popular methods. There are other methods as well for modeling dispersive media. You can take a look at the paper by Levin Savage and the DM Sullivan textbook as well.
आनंद पिछली
As with
बार आपने
FE,
पढ़ाया था आनंद तो Z ट्रांसफॉर्म से पढ़ाया था शायद ना is it the last lecture
yes,
used
in
Z
the last,
transform na?
yes, we used Z transform in the previous course. So the
Yeah,
DM
okay.
Sullivan book uses the Z transform method. The DM Sullivan book will use the Z transform method. I can't recall if it uses ADE or not. PLRC is available in the 11th Savage paper. But we in this particular course, we won't be bothered with this. We'll stick to voltage and currents on transmission lines. As with FEM, the FDTD method is not as efficient as the method of moment modeling structures containing PCs and radiating conductors because the model uses sigma values, and for PCs, the sigma is infinite, and we can't really handle infinity inside the codes. We will use high like large values, but not infinities while modeling PCs. But if your structure terminates with the PEC, for example, if you're trying to model a guided structure, in that case, it's all right because we can put the voltage value 0 or the electric field value 0 because but they become 0 on PCs. So that's how we can handle at the boundaries, but inside the simulation space, it's difficult to handle. And there has been considerable theoretical work done on higher order FDTD approaches, but they have not been very popular because we tend to complicate simple things, and we should like for general purpose FDTD code, the just The second order accurate ones that we will look at in this course is this good is all right, and we don't really need to go for higher order FTTD approaches. So that was it about the FTTD method. I see that we might run out of time for more slides that we have. So we'll quickly um, look at the finite element method and then conclude the class, and then we'll start with the fresh FDTD method in the next class. So, okay. So as with its main competitor, the FEM handles inhomogeneous materials and complex geometries with great success, and these become problems in mesh generation rather than electromagnetic theory. So in FDTD as well, if you have a simulation space which has some epsilon 1 over here and epsilon 2 over here and epsilon 3 over here and epsilon 4 over here. So this is not the problem that we will solve in the FDTD formulation. This is rather a problem of the mesh, how you mesh the structure. So if you mesh the structure properly and assign the correct epsilon values on these uh, spaces. And similarly in FEM as well, if you are using this is a sheet and you can discretize using these triangles or tetrahedral structures, and if you just assign these epsilon values correctly while meshing, so then you are all right and you don't have to worry about it because the formulation dictates that these will be solved as one structure whose dependence is calculated within Excel. So these are the so inhomogeneous materials. You'd have to just mesh correctly, and your code works all right. The FEM may be derived from two viewpoints. One uses variational analysis, another uses weighted residuals. So I'm just keeping them here so that we know that there are two methods. Since we won't be covering FEM, we don't have to worry about it. As in the previous slides, I said the FEM, you have some unknowns. The unknowns will be written in some polynomials, and then the polynomials will have some maximum or minimum, and this maximum minimum will give a solution to this polynomial, which will in turn give you the results for the unknown. So this is somewhat which I understood is the workflow in FEM, and for both of these cases, and both these cases you will start with the differential form of Maxwell's equations. Yeah, so over here we discuss the same thing. The variational function or the weighted residual, they will solve this particular function, and this function will give you the values of unknowns. And yeah, so the tetrahedrons or the triangles are the most popular way to mesh the simulation space because they are very simple. Triangles, they have just three edges and they can be used to accommodate any structure. For example, this is the structure. You can easily have triangles which can model this as well. But if you have to use squares, you will have unfilled areas, and then you have to do more approximations in FDTD. But if in case of MOM or FEM, the triangles will just fill all these spaces. Okay, so some more information of finite element method. So finite element method generally has two types of problems. One is the eigen analysis, and the other is the deterministic or driven problems. So the deterministic usually has sources or excitation, and eigen analysis is source free. So for example, if you have a resonator and you want to find out the resonance frequency and stuff, you don't really need any source. You can evaluate using the eigenmode analysis and solve stuff. So I won't go into detail of the eigenmode analysis, but This is one way you solve using the finite element analysis. The other is like the what you do in FDTD. You have the structure, you put in some source, there's a wave which travels, which reflects through other points, and then you solve. Uh, you have a source which excites the structure, and then you solve for electric and magnetic fields, and then you get the results which you want. So there's a two-way which you can solve, and yeah. So the strong points of FEM, very straightforward treatment of complex geometries because we are using triangles and tetrahedrons for homogeneous media as well. Very simple handling of discursive materials because we solve for each frequency, and in that case the wave velocity and stuff are simple because all these properties are frequency dependent. Um, we can solve eigen problems, study yourself if you want to know more. So this is in itself another course, so we won't go get into this. Slightly better frequency scaling than MOM. So this instead of 6, this becomes 5.5, which if you see if for an exponential is significant, although it does not look like significant. So it scales better than MOM, almost similar as FDTD, and but as compared to FDTD, it does not generate wideband solution in one run. It has straightforward extension to higher order basis functions, so this we'll skip this. But just to know, the FEM method uses some basis functions and things which can be scaled for higher order, unlike FDTD where higher order scaling is not good. FEM has good higher order scaling, thus which implies we can get better results. Multiphysics potentials, this means you can couple. So I think Sudeb asked that how uh, the FEM and MOM they work together. Uh, so FEM can be incorporated with other uh, techniques as well, which we call as multiphysics potential. And since both the methods FEM and MOM are very popular, there are different packages available. So I'll come back to Sudhir's question in the next class. I'll see how it is implemented. So these are the strong and weak strong points of FEM. And the weak points is again like FDTD, we do not like have good treatment of conducting structures. Um, this becomes very FEM mesh becomes very complex for three-dimensional structures. Um, but that's all right since this method has advanced quite a lot. Meshing is done by like usually mesh. We have separate design machines for doing meshing, and even mechanical engineers um, need to mesh stuff. So meshing technology has also advanced. So this is all right. But if your structure is very complex, for example, it has a lot of pointed stuff, and this is in 3D, you will need very small tetrahedrons to accurately model these spikes and stuff, and hence you will end up with more elements. And if you have more elements, means more RAM and more ROM, which is a problem because this is limited. And FEM is rather more complex to implement than the FDTT method. As we said, you have to do a lot more math as compared to the FDTT method if you are trying to write your own code. And efficient precondition iterative solvers are required for higher order elements. So if you have more elements and if you are solving for more frequencies, so since each frequency will take t time, and if you're solving for n frequencies, it will become tn time. So you might have to do parallel computing and stuff, which is not really uh, a one-person job. Okay, so I'll maybe pause over here, take questions. In the next few slides, we'll look at a couple of other methods in short, and then we'll probably end today's class and begin with more material the next class. Okay, I think I went a bit quickly in the past few slides. So all these materials which I covered are from David B. Davidson and chapter 1. So this is a very good book, and I'll recommend going through this book along with this course, because um, up until the third and the fourth class, I think we'll still be working around this book. We'll cover chapter 1 and 2. That's all we'll cover, but these two chapters have a lot of material. So the other methods are the transmission line matrix method and the method of lines. Um, in the transmission line matrix method, it is very similar to the FDTD method. And instead of directly discretizing Maxwell's equations, we use an array of short transmission lines. Um, I haven't used this method, but I'm a little familiar. So basically, you discretize the entire space in terms of small transmission lines, and then you solve for each transmission line and end up with some result. So this is how we do it. So just to know that there are other methods apart from the FDTD, MOM, and FEM, which are popular. And I I believe there is some solver also based on this. I don't recall its name. There is another method of lines. I'm not sure if it is more work is done on being this method, but this is primarily for waveguiding structures. Okay, so I think we'll stop over here because um, we are out of time, and we have quite a lot of slides more to cover, so we'll do it in the next class. We'll begin with the CEM modeling process and then the finite difference time domain method. Maybe look at the first code in the next class as well. So any questions on what we covered today and any other questions in general before we end today's class? Okay, if not, maybe I'll stop the recording and then